So I want to discuss the model which sort of has a strange property. But when you can you connect it at one point or? Sorry? Now, can you? Yeah, so I want to discuss a model which has a strange property that there are like well over 1,000 papers about it, and basically one theorem. So it's called diffusion limited aggregation. And basically, it was suggested by Witten and Sanders. So it's another Witten, not the Ed Witten of superstring theory. And as a model for several phenomena, and in fact you quite often see it in the lab. So I think the one which they actually studied was growing of some aggregates on the Teflon walls of diesel engines, funny as it sounds. So basically you have a Teflon wall, so which is very non-sticky, and suppose at one point you have a dent and some particle attaches to it. And then the model they suggested is that once you have the first particle attached, the particles, they move randomly, and if one touches the first one, it attaches itself to the first one. So you start with a second particle, it moves randomly by Brownian motion until it hits, it attaches. Then you start with the third one, and so on, and then you grow a thing which, well, it's sort of clear that it will have some sort of dendrite structure. So start with one particle. So this is like aggregate K1. To pass from K1 to Kn plus 1, start Brownian motion at infinity until the particle hits Kn, and then it sticks to it. We get Kn plus 1, and so on. So before I show some pictures, because my laptop I don't have, and Dima is working on it. So maybe I'll say a few words about what apparatus is needed to study this problem. So the distribution of the particle will be according to harmonic measure. So Brownian motion hitting probability is proportional to harmonic measure. Is it working or?
Can it just pass around the laptop?
No, but can we show it? What do you mean pass around laptop? Yeah, I don't know. Just can you attach? I mean, it's okay. Not. So and I want to show some animation. Just if you open some Chrome browser or something. Yeah. So probability is proportional to harmonic measure. And it means you are more likely to land at tips, less likely to land at fjords. So it's your basically, if you have a picture like that, it's intuitively clear that it's very unlikely that Brownian motion will go down to the bottom without hitting the walls, and it's very likely that it hits here. So I'll since we don't have pictures there yet, let's start with just some estimates. So one thing you can easily analyze. So suppose K is a polygon. So what will happen? Suppose that we have a site, well, whatever, something like this. And this angle is alpha. So how do we calculate harmonic measure there? Well, the easiest way is just to uniformize to a disk where the harmonic measure is uniform, or to a half plane, whatever. So if we take, so locally map, which maps this to a disk or a half plane, then locally you send angle alpha to angle pi. So you say the map is locally z to the power pi over alpha. So if you had here a bow of radius delta, so suppose you have here b delta, then here the image of b delta will have basically length delta to the power pi over alpha. So the harmonic measure of the bow b delta is approximately delta to the power pi over alpha. And, well, let's say, yeah, maybe it's better, I will have alpha later, let's better theta. So let me denote this power alpha. So theta can be from 0 to 2 pi. So the pi over theta, this power alpha, can belong from, so when you run from 0 to 2 pi, you have interval from 1/2 to infinity. So basically, if you have polygons, then essentially what we say that omega of b delta will be between delta to the power 1/2 and, well, delta to the power infinity 0. So at the bottom of the fjord, and the most exposed can be delta 1/2, and this is when you have a spike protruding. So this is essentially the only estimate you can prove for a given point, and anything can be realized. So this I did for a polygon. If you have an arbitrary domain, you can also prove this, and maybe let me do it. But just before I do it, I say a few words. So it's the root of only theorem known about ZLA is this estimate that omega of is always no more than delta to the power 1/2, which is trivial for corners of polygons and a bit more difficult for an arbitrary set. So in general, what usually physicists do, so the usual picture is what they call multifractal analysis. So we instead of just counting what are the possible values, we count how many of each you have. So we say that spectrum f of alpha is for a given set k, or given measure omega on set k, is f of alpha is the Hausdorff dimension of the point z, such that omega of b z delta is approximately delta to the power alpha when delta tends to 0. Of course, well, that's a bit unrigorous, that what you would do if you are a physicist. So normally if you take arbitrary fractal set, what you will have is that this omega at different scales for a given point will oscillate between different values of alpha. So for example, if you take von Koch snowflake and you take not a point at the tip but a generic point, then it will oscillate between different values of alpha. So normally you need to put lim sup here or something like that. So it's basically z, so that lim sup or lim inf of, you have to take logarithm of omega b z delta divided by logarithm of delta is no more than alpha, something like that. So if you have a nice set, so nice polygon, then the spectrum will look like that there will be dimension 1 of points where omega is linear. So it's f of alpha, it's alpha, so it will be dimension 1 of points where omega is linear. And then there will be dimension 0 of points which represent different angles. So it will be some points here, 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 which correspond to the corners. So it's not a very interesting thing. But if you take some sort of a fractal type structure, like a Julia set of von Koch snowflake, so the usual thing for the fractal will be some sort of a convex function. And what do we know about this convex function? So there are several things which we know. So first, dimension cannot go above 2 because we are in the plane. Second, the power, which we'll prove in a second, can go below 1/2. So this is the bound. So the graph is contained in this thing. It can, in principle, touch it. Then there is a theorem which I mentioned, that the Hausdorff dimension of harmonic measure is equal to 1. So harmonic measure lives always on a set of dimension 1. The bulk of harmonic measure lives on a set of dimension 1. So this is Makarov's theorem. And well, that's about it. That's about it what we can say for arbitrary sets. So there is a conjecture which implies many other things. So the conjecture is that the supremum of f of alpha over all sets k will be equal to 2 minus 1 over alpha. So it's a hyperbola which goes like that. But this is sort of wide open. Now, so what does it have to do with the diffusion limited aggregation? So we still don't know whether it is a fractal or not, because I mean, what we can analyze finite configurations. It looks like it should be fractal in the limit, but we don't know whether there is a limit. And the experiments show that its sort of spectrum is kind of non-trivial thing like that, so it has all the things, all the attributes of being a fractal. And the only theorem which exists is based on the fact that there is this estimate. So let me just prove this estimate. So for arbitrary sets, so we'll do a little bit of complex analysis before passing to probability. So the estimate is that omega of B delta is no more up to a constant delta 1/2. So it's a theorem. So it's usually said that it's Berling estimate, but it's first appeared in, so there are several proofs. Karleman, Alfors, and Berling. So those were 3 Swedish complex analysts, well, 2 Swedish and 1 Finnish. And they studied slightly different topic at the time. They studied value distribution of entire functions. And some estimates you need there, they pass to the estimates you need here. So I maybe will do the proof of Karleman, which is the shortest and the easiest, but it's a bit, so Berling's proof, if you open a book, most books now, they have proofs which use Berling's extreme length. It's an object which is kind of very nice to estimate, and once you have set it up, the proof is very short, but then it takes time to set it up. And Alforce, so what is a harmonic measure? Harmonic measure is viewed from some point. So here we view it, for example, from point infinity. So if you change the point from which it's viewed, it's a harmonic function. So we need to estimate a harmonic function with certain boundary values. So Alforce did it by constructing some subharmonic functions, and Karleman did by some differential inequalities. So basically, what is the setup? So we need to show, so we have let me maybe formulate it again. So suppose that K is connected. Diameter of K is approximately 1. Then harmonic measure viewed from infinity of bow of radius delta is no more than delta to the power 1/2 up to a constant. So it goes like that we have this set. We take a bow of radius delta, the set is size 1, and we take harmonic measure viewed from infinity. So let's say that this bow is centered at point A. Then there is a point B, which is distance 1. And infinity is the point C from which we view the bow. So what we can do, we can map, so let's say map this so that A goes to 0, B goes to infinity, and then C will go to point, well, let's say C, which is approximately 1. So it's, we'll look again at a bow of size delta, well, and the bow of size delta will go to something which is a bow of approximately size delta. So now we have a set which goes all the way to infinity, and we view it from a point C, which is distance approximately 1. And if I take a function h of z, which is harmonic measure from point z of this b delta, so what do I know about this function? So this function h is harmonic. It's 1 on b delta. So if I'm here, then I'm already, if I write it as a probability of harmonic of Brownian motion hitting the bow, here it's already equal to 1. And 0 on the rest of my set k, on k minus b delta. So I need to estimate a function which is harmonic inside, 0 everywhere here, and 1 on this bow. And I need to estimate that it is small here. So I need to estimate that it is small here. And it's slightly more convenient to do it not in an angle, because what we are going to use, you see, we are going to use that the angle is no more than the 2 pi. So it's slightly more convenient to work not with an angle, because the circumference of the circle grows, but rather map it logarithmically. So let's map it again by the logarithm map. And if we map it by the logarithm map, then the bow of radius delta, it's mapped to log delta. And then we map to some sort of a strips-like thing, which might be kind of complicated. So if you have different dendrite-like structures, which goes off to infinity. So at distance 1, so basically at level 0, somewhere you have our point C at which we estimate everything. And what do we know? We know that every circle intersects our set on a number of arcs who sum up to 2 pi at most. So we know that every cross-section, has length at most 2 pi. So the cross-section, let's say at level x as x, which has length Lx no more than 2 pi. So basically we have an infinite domain which is like a strip. Every cross section is no more than 2 pi. And we have harmonic function which is 0 on the boundary and 0 at infinity, and which is 1 here. And we want to estimate that it decays very rapidly, that here it's no more than square root of delta. I think there is one more thing which I did not mention, and one more thing is that here point C was well within a disk on a sphere of radius 1. So here it will be within a disk of radius at least 1/4 by Kirby. And here also it will be within a disk of definite radius at least, well, let's say pi over 16 by Kirby theorem. So it's at least well separated. So we have a harmonic function in a strip, and we want to show that it decays. Now, if it were a genuine strip, we know the answer, because in genuine strip, what will be the answer in the genuine strip? So in the genuine strip, here, for example, the Poisson kernel is just imaginary part of 1 over z. So when we map it, we have to apply logarithm. So it will be logarithm of z. So we have, wait a second. So when we map by so what I'm doing. So here it will be 1. Here it will be 1 over z. If we map it here by logarithm, here it will be exponent of z, so it will decay exponentially. So we cannot write, so if I just, for example, if I have a straight strip and I write something like exponent minus z, that would work very well for a strip of width pi. Because for a strip of width pi, I can have it shift exponent z so that its imaginary part on both sides is equal to 0, because exponent is cosine plus I sine, so I take sine so that it has period pi, it will be exactly like that. If I have 2 pi widths, then I will have to do this function. If I have like k pi, I have to do this function. Now, obviously, if I have an ugly domain, I can't write an exact solution, but I can write estimates starting with this exponential thing. So let me just write these estimates. So I will erase this part. Okay. So denote by the function phi of x, integral of h on this cross section. Integral of h squared on this cross section, dy. So the proof of Karl-Lehmann says that you have the following inequality star, that the derivative in x, second derivative of an x of square root of phi, is at least pi squared over length at x squared, square root of phi. You can immediately ask why where do we get pi from? If there are no circles here, we get it from, we know the exact solution. If there is a straight strip, it's an exponential function which has pi periodicity in imaginary case. So it will get it from the exponential function, from knowing the exact solution. Okay, so if we have this, so if I assume star, what do we have? We have, well, if we plot square root of phi, then what do we have? We start at log delta, and we are at 0. So we know that at log delta, square root of phi is, well, basically integrate function 1 here. So it's some constant. So here it's constant c. So actually c is equal to just length at this point. And then it's a convex function with some bound on the second derivative. So it will look something like that. And here it tends to 0. So here it tends to 0. So the minimal value, if you have this inequality, will be when there is an identity. So the minimal value, and we also know that L of Lx is at most 2 pi. So minimal value when the second derivative is at least 1/4 of square root of phi, or actually if there is an identity. Well, this equation we can solve, so it's when square root of phi is equal to a constant times exponential of minus, so it's a second derivative minus 1/2 x. And the exponential should be such that here we get a constant, so it's basically how to better put it. So here we, at log delta we should get a constant. Yeah, maybe let me. Yeah, minus 1/2 x minus log delta. So when we plug log delta, we just get a constant. So we get that the square root of phi at 0 is always at least constant exponential of minus 1/2 log delta, minus log delta plus log delta. So it's equal to delta square root so integral on this cross section of h, integral of h squared at this cross section is at least constant delta. But here, as I said, there is a definite bow where by Harmonic inequality distortion theorem it has approximately the same value. So it means that h at the point c in question squared is at least c delta, which means that, wait a second, I always wanted to do it most. Yeah, that's always just most. So h is at most constant square root of delta. So instead of evaluating at a point, we just evaluate the integral over this interval. But around this point, there is a definite bow, radius pi over 16. So if integral is small, then the value at this point is also small. Okay. And the differential inequalities just goes by using Cauchy-Schwarz inequality twice. So what we have? We have phi equal to integral over Sx of h squared. Now let's differentiate phi with respect to x. So we differentiate in the direction x. So we get twice integral derivative of h in x times h. The fact that our boundary goes up and down is not important because our function is 0 on this boundary. If you are worried about it, we can approximate our domain by some smooth curve, then it's clear that it is fine, and then just tend the approximation. But otherwise, it also follows from harmonic function estimates. Then, before I differentiate the second time, I will use this one. So this we can use Cauchy-Schwarz, which will be that well, phi prime squared is for this integral dh dx h squared, which is no more 4 integral dh dx squared times integral h squared, which is just phi. Just do it like that. So that we'll need a bit later. Let's say identity 1. Yeah. Now we differentiate the second time. And second derivative of phi is, so we differentiate second time. First we differentiate first term, then the second term. So it's twice integral second derivative of h times h plus twice integral derivative of h and again derivative of h. Now I want to estimate both of them. So the first one I can just estimate from this thing. No, let me see. What do I want to do? No, first one I prefer to estimate by parts. Yeah. So first, because Laplacian of h is 0, this guy is minus second derivative ny. So it's minus twice integral second derivative ny. Now this we can take by parts. So we move one derivative in y from here to here. So it will be twice dh dy squared. And there are no boundary terms because h is equal to 0 on boundary of our domain. So this is just integration by parts. The second term, on the other hand, we can use this estimate, so it will be at least phi is moved on the other side, 2 is here, there was 4 there, so it is at least twice phi prime squared over 4 phi, which is phi prime squared over 2 phi. And this is at least twice pi squared over Lx squared integral of h squared. So this is, well, as Karleman writes, it's an easy variational problem. I think nowadays you won't get through an editor by writing that some estimate reader has to do himself. So basically, you want to maximize integral over, so you have a function on an interval of length L, or maybe collection of intervals, and you know that it's 0 here, 0 here, and you want to maximize its integral when you give an integral of the square, when you give an integral of the square of derivative. And the optimal function is actually a sine function. So that's an easy to see thing. And here you get, because it's a sine function, here you get pi out of it. So this is a, let's say, variation exercise. Variation now. Exercise. So sine is the optimal function. So basically what we proved that phi prime prime is at least this term, phi prime squared over twice phi, plus the term 2 pi squared over Lx squared phi. So that's what we proved. And it's an easy check that it's the same as the inequality star. So it's the same as square root of phi prime prime at least pi squared over L squared square root of phi. Just differentiate square root of phi and you get that it's exactly this. Okay. So we've proved the only estimate. So usually it's called Berlin estimate, though first it was proved by Karleman, then by Alfors. And essentially it says that in the plane there are no angles more than 360 degrees. But there is a difficult proof because you might have a difficult domain. So now I will deduce from it the only theorem which there is. So people were asking, physicists were asking whether delay is a fractal. So is it a fractal? So suppose that you have aggregate n bows and diameter r diameter. So you have this sort of sticky thing. Does this work? Oh gosh. Well, just open the picture. Yeah, that's no. But why doesn't it work? It doesn't show, or
it doesn't show.
You have which HDMI?
Yeah.
Okay. Well, just should show the picture then. So what is the clear estimate? The clear estimates are obviously that if you have n bows, then n should be at least r to have diameter r if you put them all in order on a line. And it cannot be more than r squared. You cannot pack more than r bows. Now, if you put it the other way around, you can say that r is at least square root of n and at most n. So basically, well, fractional dimension. So if n is approximately r to the power a, then A is the Hausdorff dimension of DLA. So there were the computer experiments. So what they were done up to 100, at least the best I have seen were 100 million particles. So up to the 10 to the power 8 particles. They sort of suggest that A is 1.71 something something. Now, Harry-Kesten's theorem says that A is at least 3/2. Basically, it says that with probability tending to 1, as n goes to infinity, r, or expectation of r, or anything, r is no more than n to the power 2/3. So very big open problem is to show that R is some non-trivial estimate, say 1/2 plus epsilon. And slightly less big, but it also should be possible, and no one knows how to do, is to show, to improve the Kesten's estimate. Because Kesten's estimate, as we'll see in a few minutes, it just uses, so let's just put it off here, it just uses this Berlin estimate that you cannot have more exposed tips than 360 degrees. But in reality, for delay, you don't have 360 degrees tips. Because if you have delay configuration where there is an exposed tip, something will stick on the sides, and it will immediately have an angle not 360 degrees or something. But can you just pass around the picture? Yeah, that's. Actually, you can Google just delay animation, and then you see how it's formed. It's rather instructive. Okay, so let me first do an informal proof. So to pass from the size r to r plus 1, we need to stick a particle at the most exposed tip. So if you have some size r and you have your delay, to pass to size r plus 1, we need to stick particle right here in this region. So we needed to stick it around this thing. What is the probability to do this? Probability is, so we said that if there was a size 1 and diameter delta, the probability was at most square root of delta. Now we have size r, diameter 1, so probability is no more than 1 over square root of r, just rescaling. Probability is at most 1 over square root of r. So if probability getting here is 1 over square root of r, how many particles need we to throw in to stick it right there? We need square root of r particles. So from 1 to size r, we need sum from r small from 1 to r of square root of r small, which is approximately, so we integrate square root, so it's approximately r to the power 3/2 particles. At least. So hence the estimate. So there are two problems with this informal estimate. Well, one problem is that, well, not a problem, but rather a positive sign, that when we do it, we assume that the exposed point has square root of r, 1 over r probability for a new particle to land, whereas it's actually smaller. So we need more particles, so it should be possible to improve it. But to improve it, we need to show that there are no tips which have 360 degrees angle, and that we don't know. Moreover, it's a very interesting thing. So there is a paper from last year which compares DOA when done on a lattice and done in a plane. And it looks that in a lattice, at first you see exactly the same picture up to, I don't know, 10, 50,000 particles. But once you get more, usually you see the same, like Brownian motion and random walk look more like when you add more particles. But For delay, if you do it on a square lattice, then you start seeing square lattice structure when it's very large, and here the tip is sort of almost 360 degrees. Not quite, but so it's not clear. Well, it's not clear that it doesn't happen, but on the other hand, it looks like it should not. Maybe only on a lattice, because lattices have these preferred directions. But this is just a thing about improving. But about the proof itself, the problem is that we assume that there is only one point where when we add a particle, we increase the diameter. But it might be that our fractal touches this in a few points, and then the probability increases. So suppose that our fractal is a disk. Then whenever we put one more particle, the diameter increases. So this is the problem that when we first reached the size r, there was only one point where we could add a particle and increase the size. But then other parts grow, and as we add this square root of r particles, we can get more landing points which would increase the size. So one needs to do some accounting for that. So I will do this accounting. So let's go without break because it will take 10 more minutes only. So the accounting is not very difficult. For some reason, I looked yesterday. There are a couple of books where there's written up, and everyone just copy-pasted the accounting done by Harry Keston, which is, which is not the shortest possible. So basically, let's do the following thing. So we have delay of size r, and we estimate probability that 2r reached from r after adding r to the power alpha particles. So we start adding particles, we add particles, it grows, and we estimate that probability that we reach size twice r after adding r to the power alpha particles, and let's say that let alpha be smaller than 3/2. And we'll see that the probability is very, very small. So suppose that let this be the first time we hit ball of radius 2r. Then this particle was attached to some particle, which was attached to some particle, which was attached to some particle. So there is a string of particles which were attached in order. So there is this sort of string of particles. So let's say length L, which is at least r, string of particles. Now superimpose lattice, a square lattice. So superimpose so this string, let's call it gamma. So gamma gives a self-avoiding walk on square lattice from BR to B2R. So it's just we can do it as a sequence, as a sequence of steps on this lattice. So it's some sort of discretization. And now I can estimate my probability. So I will write immediately a small remark. So my result will be of the form, result will be of the form r to the power minus constant r to some power. So this is a very, very small number. If r is big, r to the power minus r is very, very small number. So it kills all the things like r to the power a and b to the power r. So all such things will be killed. So this is much small number. It kills these things when r is large. Because in this one is exponential, one is polynomial, and this is exponential of r. So I will just forget such things immediately. When they arise, I forget them. It just means that for r large enough, they are immaterial. Okay, now this probability is can be estimated as the following thing. Then first, this length L can be different. So we need to sum for L what is the minimum possible length r, and the maximum possible is r to the power alpha. Now, if we have r to the power alpha steps, we need to choose which steps belong, which both belong to this curve. So it's number of ways to choose L out of r to the power alpha. That's the first term. Then we can start at different points on the circle. So number of start points. Then number of self-avoiding curves of L self-avoiding curves. And the rest is probability to get exactly gamma. Well, instead of summing, I can just take the maximal term and repeat it many times. So it's at most r to the power alpha maximum over L of what I can get. And remember, all such terms are immediately killed. So this is, we immediately forgotten. Now, number of ways to choose L out of r to the power alpha is r to the power alpha choose L. Well, we'll calculate it in a second. Number of start points, well, it's basically twice pi r, immediately killed. Number of self-avoiding walks, well, if you have a self-avoiding curve on a lattice, you have at most 3 directions to go at each step. So it is at most 3 to the power r. Well, again, it's killed immediately, not important. And this is what we had. This is a Berling estimate. It's 1 over square root of r to the power L. So basically up to, so this means that up to such terms, so it's up to r to the power a, b to the power r, we have that it's at most maximum in L, r to the power alpha choose L, 1 over square root of r to the power L. Now, well, how do we usually estimate the binomial coefficient? So we just use the Stirling formula if you haven't done, so everyone knows Stirling formula, yes? Well, n factorial is what is it, square root of twice pi n, n over e to the power n. Now, in our terms, since we forget such things, so in our case, it's just n to the power n. because we forget these terms. Well, it's if we forget r to the power a, b to the power r, then it's n to the power n. Now r to the power alpha over choose L, it's r to the power alpha factorial, r L factorial, r to the power alpha minus L factorial. So let me for simplicity write that L is equal to r to the power beta. Yeah, that will be better. So then r to the power beta, so what do we know? That beta is at most alpha, at least 1. So this is approximately r to the power alpha, r to the power alpha, over r to the power beta, r to the power beta, over r to the power alpha minus r to the power beta, to the power, well, to the power r to the power alpha minus r to the power beta. So I will eat up a little bit from this formula. So this is the usual thing. You split it into this power and that power. So you get r to the power alpha, r to the power beta, r alpha minus r beta. So this is part of this which went here, and this one. And this and that you put in the same power times r to the power alpha over r to the power alpha minus r to the power beta to the power r to the power alpha minus r to the power beta. Which actually is better written as 1 plus r to the power alpha, r to the power alpha minus r to the power beta. And by, there is this usual thing that 1 to the power plus 1 over n to the power n is approximately equal to e. So you use the same thing here, and if you use the same thing here, it's r to the power alpha. So this thing is approximately equal to what? E to the power r to the power alpha, which we forget. Yeah, actually we should forget b to the power r to the power a also, yeah. So we need to forget such things, yeah. So this is again forgotten. Yeah, b to the power r to the power c, yeah, so also forget. So basically what we get is that it's maximum for beta between alpha and 1. And the first term we get was r to the power beta, r to the power alpha minus r to the power beta. And the second L is r to the power beta, so minus 1/2 r to the power beta. Am I correct? Yes. So it's the maximum r to the power beta r alpha minus beta plus 1/2 r to the power beta. Wait a second, I think I miscalculated something. No, I shouldn't have r to the power alpha at all, should I? I shouldn't. Wait, so it says here that I have, oh, it should be the other way around. Oh, gosh. Yeah, I should have, unless I r to the power so I have it written here r to the power beta times alpha minus beta. Yes, yeah, of course, because we take this power out of here. Yes, yeah, sure. So we subtract this power. Yeah, sorry, yeah, because this power is split as this power is split is alpha r to the power beta plus alpha r. Yeah, okay, so it's split like that. Yes. Well, never differentiate in public. Yes. R to the power beta times alpha minus beta. So r to the power beta times alpha minus beta. So r to the power beta times alpha minus beta minus 1/2. Yes. And of course, the minimum will be when the beta is minimal. So it's at most r to the power beta alpha minus 3/2, which is r to the power r beta epsilon with minus sign, because alpha is smaller than 3/2. Okay, so the probability, if we fix power smaller than 3/2, probability to reach in that number of balls from r to 2r is super exponentially small. And then if we repeat it for every scale from r to 2r, from 2r to 4r, probability of reaching with this number of balls is super exponentially small. This probability, they sum to some convergence series with very, very small sum if you start with very large r. So by Rel-Cantel, it means that basically with probability close to 1, you, on every scale, you don't reach that number of steps.
How did we kill e to the power r to the alpha?
It's just smaller than this, because here it's r to the power something, and here it's e to the power something, and r is much larger than e. Wait a second. Is it? Yeah, well, let me see. Okay, strictly speaking, it's maybe I leave it as an exercise. Yeah, strictly speaking, I mean, first of all, the number. So what do we have? Well, the number of if you have yeah, okay. Yeah, maybe you need to do here one small trick, because if you have a constraint that the diameter of your walk is no more than r, and it's self-avoiding, anyway, there will be at most exponential number of those, because it's constrained to be in a box of size r. Yeah, so maybe I need to use estimate not for self-avoiding walks, but of how many simple curves are there in a box of size r. And that also will be that. Let me just. Okay, let's have a break. There are exercises there, and I will see meanwhile what is the good way to kill it.